Welcome students, welcome to your introduction to solid mechanics class. This is Jagdeep sir. So let's compare the solid and hollow shaft. Okay, first we are going to compare the solid and hollow shaft by the strength. Here you can see this one is the solid shaft and this is the hollow shaft. The diameter of the solid shaft is ds, length is l. The diameter, the outer dia of the hollow shaft is dh, internal dia is small d suffix h. Length is same, the length of the both of the shaft is same. Torque transmitted by the solid shaft is ts, torque transmitted by the hollow shaft is th. So now we can write, the shear stress for both of these shafts, because uh, also one thing, the material of these two shafts are same. Suppose if we consider the steel, then both these two shafts are made of steel. If we consider copper, then both these two shafts are made of copper. If we consider aluminium, then both these two shafts are made of aluminium. Okay, just like that. Okay, the material is same, the shear stress is same for both these shafts. So now we can write ts is equals to, we already know that, tau into pi by 16 ds cube, and th for hollow shaft is equals to tau into pi by 16 into capital DH to the power 4 minus small dh to the power 4 divided by capital DH. Okay, now we are going to take a ratio of these two torques, that is, we can write strength of hollow shaft by strength of strength of a hollow shaft to strength of a solid shaft, that equals to that equals to th by ts. So we can write th by ts is equals to this value, uh, tau into pi by 16 into capital DH to the power 4 minus small dh to the power 4 by capital DH divided by tau pi by 16 into ds cube. Okay, so you can cancel out these two things. You can write dh to the power 4 minus small dh to the power 4 by capital DH into ds cube, that is th to ts is equals to this. We can write, okay, let let the capital DH by small dh is equals to n. If we divide the value of capital D to small d, then we get a number or a value, a constant. That means the outer dia is n times of the inner dia. The outer dia is n times of the inner dia. Now we are going to substitute this capital DH value to this equation. Okay, so see what happens. So that is equals to TH by TS is equals to n to the power 4 small dh to the power 4 minus small dh to the power 4 by n dh ds cube. Okay, so now we can write dh cube into n to the power 4 minus 1 by n ds cube. Okay, now as the weight, material and length of the both shafts are same, as the length, weight and material, that is the value of the density, of these two shafts are same, so we can write, that is okay, so let's explain the thing. So WH equals to WS. WH is the weight of the hollow shaft is equals to weight of the solid shaft, and we know that weight means mass into G. Here the mass of the solid shaft into G. These two G are the constant, that is the gravitational acceleration. The mass means what? Mass means density into volume. Okay, so let's volume is and the volume is the area into length, area of the hollow shaft, AH, into length, this is the volume, into the density, that is rho h, and that is equals to the volume of the hollow shaft, that is area into length into density of the hollow shaft. Okay, but from the assumptions the material are the same, that means the density of the hollow shaft and the solid shaft is same, so cancelling out both side, length is same, so what we got, one second, that is AH is equals to AS, that is cross sectional area of the hollow shaft is equals to the cross sectional area of the solid shaft. So we can write pi by 4 dh square minus small dh square is equals to pi by 4 capital DS square, or we can write this is equals to dh square minus ds square. Okay, now again ds cube is becomes dh square minus dh squared root under okay, This is the relation between the solid shaft, the cube, cube of the diameter of the solid shaft is equals to uh, the diameter outer dia of the hollow shaft square minus inner dia of the hollow shaft square, the difference between these two, into root under the dh square minus small dh square. Okay, so now we are going to substitute the relation between the capital DH with this small dh. We are going to substitute the relation, that is n square into dh square minus dh square into whole square minus d square. Okay, so now what we'll get, that is dh cube into n square minus 1 into root under n square minus 1. So ds cube is equals to inner dia of the hollow shaft cube into n square minus 1 into root under n square minus 1. Okay, so now we are going to substitute this relation into the torque relation, that is dh by ds is equals to dh cube by n to the power 4 minus 1 by n dh cube into n square minus 1 root under n square minus 1. Okay, so by simplifying this relation we get n square plus 1 by n into n square minus 1. Okay, so th by ts is equals to n square plus 1 by n into root under n square minus 1. And from the geometry obviously we can see that dh is the outer dia is obviously greater than the inner dia. Okay, and this dh by small dh equals to n is obviously greater than 1, right? Is obviously greater than 1. So suppose if we assume the value of n is equals to 2, so the value of this hollow shaft and the value of the hollow shaft and solid shaft torques becomes n square, that is 2 square plus 1 by 2 into 2 over 2 square minus 1, that is equals to 1.44. so from this concept we can write, that is torque transmitted by the hollow shaft is obviously greater than the torque transmitted by the solid shaft. So we can say that the hollow shaft is stronger than the solid shaft. Thank you. Students, after comparing the solid and hollow shaft by its strength, let's compare this hollow and solid shaft by its weight. In this case, it is assumed that both the shaft have same length material. Now, if the torque is applied, both the shaft is same. That means TH is equals to TS. Okay, then the maximum shear stress will also be same in both the cases. Okay, so now the weight of the hollow shaft by the weight of the solid shaft is equals to that is WH by WS. So that becomes the AH by AS, and how this that weight is equals to the ratio of the area that we have already done in the previous section. So that is equals to pi by 4 dh square minus small dh square by pi by 4 into ds square. And we know that this thing that we have done in the previous comparison, that is dh by small dh is n, and which is obviously greater than unity. So the ratio of the weight WH by WS is equals to so the weight of the hollow shaft to weight of the solid shaft is equals to n square by dh square minus dh square by the capital DS square. So we can write that is dh square into n square minus 1 by ds square. Okay, fine. Now as we have assumed that the torque are same, that is ts equals to th, so we can write from the torsion equation that is tau into pi by 16 ds cube is equals to pi tau by 16 dh to the power 4 minus small dh to the power 4 by capital DH. Okay, and ds cube, this becomes dh to the power 4 minus dh to the power 4 by dh. Okay, okay, now the substituting the value of dh, let's see what we get. Small n to the power 4 small dh to the power 4 minus small dh to the power 4 by dh. In dh, sorry, this is the value of ds. Okay, so ds cube is becomes dh cube into n to the power 4 minus 1 by n. Okay, so ds is becomes dh to the power dh into n to the power 4 minus 1 by n to the power 1/3. Okay, now again we are going to square both the side, so ds square is equals to dh square n to the power 4 minus 1 by n to the power 2/3. Okay, now we're going to substitute this dh square value into the weight relation. That means wh by ws is equals to, we can write dh square into n square minus 1 by dh square to the power 4 minus 1 by n to the power 2/3, cancelling out, so that becomes n square minus 1 into n to the power 2/3 by n to the power 4 minus 1 to the power whole to the power 2/3. That is wh by ws. Again, we know that the value of n is obviously greater than unity, and let's assume the value of n is 2. So wh by substituting the value of n, that is 2, wh by ws is becomes 0.7829. so that means we can say that for a same material length and given torque, the weight of the hollow shaft will be less than the weight of the solid shaft. So hollow shaft are more economical than the solid shaft. Thank you. Okay students, let's see if we connect the shafts in series. Here we can you can see the connection of these two shafts of length L1 and L2. The modulus of rigidity is G1, and second shaft, the modulus of rigidity for second shaft is G2. The polar moment of inertia are J1 and J2, and the torques are the same, but the torques are the same. Okay, so this kind of connection, the shaft connection, is called the series connection. Okay, if we connect the shaft in series to transmit some torque, then the angle of twist is the sum of the angle of the twist of the two shafts are connected in series. That means the total angle of twist, that is theta, that is equals to theta 1 plus theta 2. Theta 1 is the angle of twist for shaft 1, and theta 2 is the angle of twist for the shaft 2. Okay, and this theta 1 value is T into L1 by G1 J1 plus T into L2 by G2 J2. So we can write theta equals to T into L1 by G1 J1 plus L2 G2 J2. Okay, this is J, not J2. Okay, and if we take the same material, the shafts, if the shafts are made of same material, then we can say that this G1 is equals to G2. Similarly, so this equation becomes T by G into L1 by J1 plus L2 by J2. Again, if the length of these two shafts becomes same, that means if L1, if we consider, or if we take two shafts of same length, that is L1 and L2 are same, then also we can write theta equals to TL by G into 1 by J1 plus 1 by J2. Okay, so this is a relationship between two shafts if they are connected in series connection. Okay, this connection is called series connection. Okay, let's see if the shafts are connected in parallel. Okay, this is the connection. If the shafts are connected in parallel, the both end of this connection is fixed. Okay, you can see the both end is fixed, and if we apply a torque in the middle of these two shafts in clockwise, that is here as shown in figure, and then the torque that will arises at the both end of these two shafts is in anti-clockwise. You can see uh, in this fashion. Okay, suppose this is a shaft. Okay, now we are applying the torque on the shaft, and the direction of the torque is different for both these two end. Okay, in my right hand side you can see the direction is anti-clockwise, and in my left hand side the torsional direction is clockwise. Okay, so if we apply the torque in clockwise motion in between these two shafts, then the torque that will that will arise at these two fixed end will be in anti-clockwise fashion. Okay, so and the twisting moment the angle of twist, that is theta 1 and theta 2, will become equal, and that these two are the angle of twist, these two become the equal. So from this relation we can write, that is T1 by L1 by G1 J1 is equals to obviously T2 into L2 by G2 into J2, and the total torque, that is capital T, is becomes T1 plus T2. Okay, and if the model of rigidity, that is G1, if these two shafts are made of same material, then G1 and G2 are same, then we can write this equation. As that is T1 L1 by J1, that is equals to T2 L2 by J2. Okay, so this is the connection if two shafts are connected in parallel, the both two ends are fixed. Thank you.